Hello and welcome to my video, lesson 6.1 and 6.2, characteristics of exponential functions. So first of all, what is an exponential function? Here's the general form or the parent form of that type of equation. But let me just show you an example equation where we have y equals 2 to the exponent or to the power of x. So an exponential function has x as an exponent. In a polynomial function, we normally see x as the base. Well, we always see x as the base, and we have the exponent as the number. But now we're seeing the reverse of that. And it changes our functions quite a bit, our equations, our graphs quite a bit. So y equals 2x is an example of an exponential function. So let's take a look here. If y equals a times b to the x, so that means that b is the only thing being having the x exponent. Okay, b has the power of x. A is just multiplying to that. How can we tell from there any information about our x-intercepts, y-intercepts, and behavior domain range? Well, for all exponential functions, you have 0 y-intercepts. Okay, you don't have any unless you do a transformation to them. Okay, so a transformation being something like if you have a -1 here, or whatever, like -2 or whatever the transformation might be, that could move your whole graph vertically up or down. So if we do have a transformation, which we don't look at the beginning, that would be giving us an x-intercept. But generally speaking, we don't have x-intercepts. Okay, so we'll have to look at what that means and what that looks like in a second. What about y-intercepts? Well, we do have y-intercepts. So y-intercept is where if x equals 0, right? If x equals 0. So if x equaled 0, let's just take this example here, right? If x equaled 0, it would be y to the 2 to the power of 0. So if you remember what the exponent 0 means, or what any exponent means, it means 2 to the times 2 times 2 times 2, however many times the exponent tells you. Now it says times it 0 times. So what does that actually end up meaning? Well, that means this is 1. Okay. So if the exponent is 0, that part of our equation is going to be 1. Now, if we put an a value in front, so imagine you put a 3 here times 2, 3 here times 2, it'd be 1 times 3, or it'd be 3. So you can see how our a value is our y-intercept. Again, unless you have a transformation of some sort. Okay, the end behavior is given by b. So if b is if b is fraction, or if b is greater than 0, okay, so greater than 1, sorry. If b is greater than 1, then it's going to go upwards. So I'll just draw what that looks like right now. So that means it's going to start really, really small and going to go up like this. Okay, and if b is less than 1, then it's going to do the opposite, which means it's going to start off really, really tall and then go closer and closer to 0. All right, so end behavior given by b. Okay, the domain is always going to be the same. which is that x could be any real number, because you can imagine that our arrows are going to infinity both directions for the purple and the red graph here. And our range is given by if a is positive. Okay, so if a is greater than 0, if a is positive, then our range is y is positive. If a is less than 0, then our range is less than 0 as well. All right, so two really important things to keep in mind here. Our y-intercept is given by the value of a. Our range is given by the positive or negative part of a. And the shape of the graph is given by b. Those are the three things to look at. The x-intercept being 0 is just common along all of them. Domain being any x is the same along all of them. Okay, let's take a look at some table of values and see if we can tell which ones are exponential functions and which ones aren't. So let's just see if we can find some sort of patterns here. So from here to here, or from here to here. So if we look down this line here, we add 2, we add 2, we add 2. If you can see an adding pattern like this, then you have a linear equation. Okay, and if you go to the 0 point, that would be our b value, and this is our m value, if you think about y equals mx plus b. So just interesting. But that is a linear equation. Okay, if we look at the next one here, we can see add 3, add 5, add 7. So there's a pattern, but it's not really the same the whole time. It's like a pattern of all odd numbers. But let's see if there's a pattern this way. Oh yeah, you times it by itself. You square it, right? This is a quadratic, the base quadratic. Okay, but you can see the pattern going from left to right. And this one here, what can we tell? Well, what's happening here is we multiply by 2, multiply by 2, multiply by 2 every time. This here is an exponential. Exponential function with a base 2. Okay, the number that we're multiplying by, that is our value. So this actually, if you if the base is the same as the point in where x is 1, if those two are the same, then that's all you have. So base 2 dx. So this is that equation. And I guess if we wanted to show all of them, I guess I can show all of them. 2x plus 1. Okay, and then this last one here, we also see a pattern, times 3, and you might have to check it in your calculator, but it should be times 3. So if that is a multiplying pattern again, then it is exponential. And because it's multiplying by 3, it's base 3. But our initial position here is not right. So let's go back to our x-intercept, right? So divide by 3 to go this way, right? So then we should have 2. Okay? So whatever that point is, right? So y equals 2 times by 3 to the x. So our y-intercept there is the 2. So the 2 ends up there, and the multiplying by 3 ends up here as the base. All right, so just from a table of values, you can very quickly make exponential functions. They're actually a little bit easier than quadratic functions to make. Let's take a look at general rules about them. Looking at values of a and b, what's it going to look like? Because we talked about the range, we talked about the shape or end behavior, but what's it actually going to look like? So let's start with a blue one. So if a is positive, the whole function is in the quadrants 2 to 1. If a is negative, the whole function is 3 to 4. Okay? Or y is positive versus y is negative. Okay, if b is greater than 1, the function curves up towards infinity. If b is less than 1, it curves down towards 0. Okay, so let's take a look at what this looks like. So here is our function. It's going to look something like this. Wow, my hand is not very steady right now. There you go. That's closer. Okay, and based off of this function, the only point that we really actually know is that the intercept is that, because a value is 1. Okay, whereas if a is negative, right, it's going to be the same function except -1. And so how we can draw this, or perhaps I should do this in red. Okay, so 0, -1. So it's just the flipped version where it's reflected in the x-axis. Okay, what about fractional b values? Because they're supposed to do something different. They're supposed to change the shape. So instead of curving up, what's going to happen? Well, we are going to curve down. So still the same a value. Right? But that's really annoying. Okay, stop it. Okay, it's curving that way. It's curving up. This. Again, it's not perfect, but it's hopefully close enough. So you get a good idea of what this should look like. You kind of have to imagine a perfect curve. There you go. So now we can see that if it has a positive a value but a fraction, it's like this green graph. Actually, maybe let's zoom out so you can see all four at the same time. So the a value determines whether or not it's going to be on the top or the bottom. And the b value, if it's a whole number, it's going to be curving towards infinity, whether that be negative infinity, right, or that's positive infinity. It's still curving towards infinity. And in both of these cases, it's going towards 0. So it's getting closer and closer to 0, but never actually touching 0. And that's why we have no x-intercepts, because it's not touching 0. It always gets closer, but never touching 0.